Hi, everybody. It's great to be here. I am actually snuck into this program by the back door because I'm in the Kinetics 24 program, but then they asked me to talk at this meeting, so thank you very much for inviting me so I could meet everybody at both programs. It's a busy week. Jorge, thank you so much for giving such a lovely talk in my place. I do not know if I can reach the same bar, but we'll try. Thankfully, Jorge and Ozzy also basically gave you a primer on all the simulations that you need to know about for this talk, so I get to skip more or less straight to the point. So I think rather than tackle this entire broad topic in 20 minutes, what I'm going to do is focus on one thing that seems to be of interest to a lot of people at this meeting, and then I'll give you some teasers for other stuff you can ask me about later. So my real talk is about the cosmological context of stream and subhalo interactions. So as you know from previous talks and all the great work that many of you have done, one of our best hopes for constraining the low mass subhalo mass function, which is a direct prediction of dark matter models, is to look for the evidence that those things interacted with tidal streams, which are very dynamically cold, so they're very sensitive gravitational accelerometers. So there's one word in my original title, the zoom word, that you maybe aren't as familiar with. This is a movie from one of the cosmological simulations of a Milky Way mass galaxy that I'll be using in this talk. So as you can see, it's got an assembly history, it's got a disk forming in the middle, all that stuff. So what makes this a zoom is that somebody once ran a gigantic dark matter only simulation with a jillion halos in it. And then what we did was go back and find a Milky Way mass halo, so that means something around 10 to the 12 solar masses within that low-res simulation. And then what the zoom does is resolve that same thing at much higher resolution, add the gas particles that will then form the stars, and then also add the large-scale sort of tidal forces that come from the larger scale structure that isn't within the box that created the halo. So you're essentially taking a piece out of the Planck initial conditions and getting as much of that structure into that piece so you can resolve it at the resolution that you need in order to see what happens to stars and gas in that galaxy. All right. So these are all from the Fire suite, and they are all run with the same stuff that that Jorge just told you about, so I don't have to go back over that. And these simulations allow us to confront our models, generally speaking, with some realism. So of course, every simulation is wrong in some way or other, right? But the realism that I'm referring to here is specifically the cosmological context and the live interplay between baryons and dark matter. And so for extreme subhalo interactions, this affects our predictions for what the frequency of those interactions should be at a couple of different levels that I'll talk about in a couple different ways, and sort of at the factor of 2 level compared to idealized models. It affects other things in different ways than this particular prediction. So just to give you a teaser, this is not a globular cluster. This is a satellite turning into a tidal stream in one of our cosmological simulations, and all the little red dots are subhalos that come within 2 kiloparsecs of the stream. So you can see that they show up right when they pass through that thing, and I have not labeled them by mass, so a lot of these are tiny. They have no effect on the stream except tiny little kicks to individual stars. But some of them are big and could create disturbances that we might potentially see, especially if this weren't a satellite stream, but a globular cluster stream, which is much kinematically colder in most scenarios. And I'll get back to that right at the end. So the goal, of course, is to take this beautiful observations that people like Anna and Adrian are doing and translate those into this, which is the number of subhalos of a given solar mass, and then connect that back to like the cross section of the dark matter particle, right? So that's like the end game here, right? But there's a lot of steps in here, and this is where we need cosmological simulations in order to get from here to here. Okay, so people have already made steps down this road. The rate at which you expect these encounters to happen depends on the phase space distribution, so the distribution of the subhalos in position of velocity, and also the phase-space distribution of the streams in position of velocity. Because if you'll notice here, so this thing depends on the relative velocity between the subhalo and the stream. Right? And so the way that this goes generally is that a lower relative velocity will produce a larger effect. And so the most effective disrupting subhalo encounters are the ones where VREL is the smallest. That's not encapsulated in this expression. This is just about the frequency of stuff at any mass. The stream phase-space distribution also comes in through these two variables, which are the length and width of the stream. And so those are dependent on how long the stream has been around and how big the thing is that produced it. And then finally, the subhalo phase-space distribution comes in a number of other places. So there's the density of subhalos as a function of where you are in the main halo. And of course, the velocity distribution comes in through the relative velocity. And then this Bmax is sort of the like maximum viable impact parameter, so the maximum closest approach that you can get to cause an effect that you could potentially observe. And so this convolves the history, the like for hierarchical assembly history of your galaxy, which gives you an idea of what distributions you think of for the ages of the streams and the population of subhalos you have with the dark matter physics. All right. So what people do in general is that they assume an isotropic subhalo distribution in position of velocity. So the density can vary with radius, but it's generally considered that the distribution is isotropic. Oops, sorry. They also assume, and this is an extremely useful simplifying factor, that there's no bulk motion of the subhalos relative to the streams that they're interacting with. So the mean relative velocity is 0, but you can have stuff that has relative velocities in either way. This is not the same, sorry, as saying that the most common relative velocity is 0. All right. So we went and checked in our simulations to see how good these were as assumptions. All right, so this was work that was started by Nand Pandisan-Paisal, who is now a postdoc at Carnegie and is the one that Jorge was talking about, looking into these galaxies. So when you look at the and so what these are distributions of different things that are substructure in the halos across all our simulations. There's like 13 of them. And this parameter cosine theta is the angle between the orbital plane and the disk plane of the galaxy at the present day. All right. So if the distribution were isotropic, then the distribution would be flat in this parameter. And you can see that there's some slight variations. Subhalos in the simulations like to be either polar or coplanar with the disk by a little bit. All right. It would be nice if this were reflected, say, in the present day distribution of satellite galaxies, so that we could measure the one and then infer the other, but that it doesn't seem to be the case. So the present day satellite galaxies seem to prefer prograde over retrograde orbits at the poles. And that's partly because disks are good at disrupting things with certain angles relative to their orbits, but not others. So if you look at the progenitors of the things that are now tidal streams, so these are the things that got destroyed and removed from the bound distribution, then you see that those like to be on polar orbits, either prograde or retrograde, but not in the middle at sort of like a 45-degree angle to the disk, because that gives you a lot of, that's a more effective way to tidally disrupt your system. All right, so this is telling you that this assumption is moderately good, but not perfect. And then we looked at what's happening to, okay, so this also, wait, let me go back. So this means that like tidal disruption is selectively eliminating some subhalos from the population. And it has a follow-on effect in the relative velocity distribution because the stuff that is more radial gets stripped more effectively. And so there's a, let me see if I can get this here. Yes, okay. So this top like light dashed line for black and pink are two different simulations. That's the distribution of the subhalos in those two Milky Way mass galaxies as a function of their tangential velocity. So low tangential velocity means a radial orbit. High tangential velocity means a circular orbit-ish. And so when you add the baryonic component to the middle, when you add a growing galaxy in the middle, then you get these solid lines instead, and they are preferentially depleting the stuff at low VTAN, right? So this means that the relative velocity distribution of your remaining subhalos is missing a bunch of the ones on radial orbits. And that changes it from being isotropic. Okay, so all of this so far has been with scenarios where the present day halo in our simulation is pretty much sort of like hanging out. It's not having any major interactions, but of course our Milky Way is merging with the Milky Clouds. These are formerly known as Magellanic Clouds, but I like the new terminology better. And so here's a beautiful view from David Diver's work of the gas associated with the two clouds. The small cloud is about 10 to the 9 solar masses now. The large one is about 10 to the 10, but was probably about a factor of 10 larger, and therefore a tenth the mass of the Milky Way when it showed up in the system in the first place. And this really nice work by Nico Garavito Camargo has shown that this does all sorts of weird shit to the Milky Way. So you can see, first of all, that it adds dark matter debris. This is from Nico's model, which is an idealized model of this that's calibrated to our best measurements of the orbit of the LMC from proper motion measurements by Gertina Besla and Nithya Kadavalil. And it also drags some dark matter along with it in a dynamical friction wake. And then it also makes the center of the Milky Way slosh around, because now you have sort of a 1 to 10 thing, so it's almost like a restricted two-body problem, where the center of mass is not at the center of the Milky Way's light anymore. It's not at Sagittarius star, right? So there's some responsive motion, and that sloshing creates this other overdensity up here that's called the collective response. Okay. So we have a simulation that has an LMC-like thing happening to it. It happens at about redshift of 1/2, which is a little bit early, but is close enough that we're going to go with it for now. And it actually has quite a comparable orbit to what we think the actual LMC is doing. So the red is our LMC analog simulation. The blue is Nico's model of the LMC's orbit. And then these are some distributions of the dark matter in different projections. And we're going to come back to these quadrants later. So to give you an idea of where we're going, we're going to be evaluating more of this isotropy assumption. And so these quadrants, 1, 2, 3, 4, are things we're going to compare to like see whether the effect this merger is having is different in different directions in the galaxy. And at the pericenter, the LMC analog is in quadrant 4. All right, so the first thing that happens when you do this is, of course, the LMC contributes a bunch of its own subhalos. So the red ones are the ones that came in with the LMC. And at some times, this is going to contribute to the anisotropy of the density distribution of the subhalos. All right? But eventually, things sort of mix together. The black ones are all the things that were in the Milky Way before. All right? So this is mainly important until like just after pericenter, which just happens to be where the LMC is now. Most of the new subhalos, since they follow the general scaling, are below 10 to the 7 solar masses. The LMC is a 10th the mass of the Milky Way, so its most massive halos are 10th the size of the ones in the Milky Way, and so that's all borne out in the augmentation of this distribution. All right, but that leaves a lot of them that are sort of in the sweet spot for subhalo detection, which with streams, which spans, the 10 to the 7 to 10 to the 8 regime. All right. It also messes with the phase-space distribution. So these are contour plots at different times. So 0 is pericenter. That's a gigayear before. This is a gigayear after. The brown in the background is the phase-space density of all the subhalos in the Milky Way, and the green contours over top are the ones that came in with the LMC. So at first, the phase-space distributions are really different, but I settle down after a while. All right? But this tells you now that the velocity distribution is not isotropic during this interaction. All right, the second thing is that the response that the Milky Way has to the merger, right, is spreading these effects over the entire galaxy as the interaction continues. So what you're seeing here in blue is the velocity of the center of mass of the Milky Way galaxy, excluding the LMC, in the big cosmological box. So the actual normalization of this axis is arbitrary, but you can see that over pericenter, there's a big swing in the velocity. Whereas if you look at one of our simulations like this green line M12I, which doesn't have a Milky Way interacting with an LMC in it, then you don't see these kind of big swings in the velocity. So that's the reflex motion, as it's called, of the Milky Way to the LMC in the merger. And you can also see here, this is sort of the direction. This is where the LMC analog is on the sky. Here it is at pericenter, and these triangles are the direction that that velocity is pointing as a function of time. So not only is the velocity changing, so not only are you now in an accelerating frame, but also the direction of the acceleration is changing with time. All right. And so this sort of sloshes everything around a little more. And the effects here can even be larger than the ones that come from the subhalos that LMC came in with. Because they're rearranging the phase-space distribution of the subhalos that were already in the Milky Way. There's going to be more of those because the Milky Way is larger. All right, so this top panel is for reference, showing you which quadrant the LMC is in at a given time and where it is in distance from the main halo. All right, and then this quantity sort of measures how anisotropic the velocity distribution is. All right, if you want to know how that works, you can read the paper. I won't bore you with a lot of equations. So the blue line is what that anisotropy is doing. And the pink line is the anisotropy of the subhalos, excluding the ones that came in with the LMC. And this curve is calculated by following the LMC through this curve in the middle is calculated by following the LMC through whatever quadrant it's in and patching together what this anisotropy is in the same quadrant as the LMC is. The bottom one is following the polar opposite quadrant of the LMC and doing the same calculation. And so not only does the LMC itself shift the Milky Way subhalos around, because the purple dashed line and the blue line are almost the same, but opposite the LMC, later on you start getting this sloshing that introduces anisotropy in the direct opposite direction in the sky. So this response is not dominated by the LMC's contributed subhalos, it's dominated by the back reaction of the Milky Way. All right, so the bottom line is that you get some significant deviations in the bulk velocity of the subhalos, so the mean relative velocity is not symmetric or about zero. And when you add those deviations into the calculation for the interaction rate, it'll increase the interaction rate, depending on which quadrant your stream is in, by up to 75%. So that's what's shown here. The different colors are the different quadrants. The gray line is with the basic assumptions, isotropic position, or isotropic density of subhalos, isotropic velocity distribution. And by isotropic here, what I mean is we spherically averaged the one from the simulation and used it to calculate the interaction rate using the equation that I showed you before. And then the dashed lines are if you still assume a mean velocity of 0, but you include the other anisotropies I talked about. But this top line is when you include the bulk velocities. All right, and so that means that there are places in the sky where you should look if you want to find more subhalos from the LMC and increase your chance of detecting a thing that could have interacted with a subhalo. And so here's a sketch of where that is. This is a little bit schleppy because what we did was just rotate the interaction so that the LMC was at the same place in the sky as the present day. And so that So our orbit is actually a little different than the Milky Way's with respect to the disk of the Milky Way. So there are some differences in the orbit. So this is more of a schematic than a like go point your telescopes here plot. But I think it's worth re-examining this with a built-in or like a model of the LMC interaction that is more tailored to the exact specifics of the orbit. All right, so I will give you a preview of two things and then I will shut up. So one is, I talked about how this would all be better if we could do this with globular clusters. So what we're working on right now is trying to use the work that Mike Grudich and Carl Rodriguez did to identify formation sites of globular clusters in simulations and follow them through to determine their orbits, and then use Carl's machinery to calculate the exact positions and velocities of stars as they're stripped from the systems. And this is work that's also being done with Jitske Starkenberg, Sarah Pearson, who's here, and Vanessa Pascal. And one of the things that we found that was really surprising first was just that the mass of the star determines where it's stripped. So massive stars get stripped when the thing is close to pericenter, but as you go down in mass, you get a broader range, and this is a function of the mass segregation of the cluster since the lighter stuff is on the outside. And that implies that the length of the stream, and therefore your inferred formation time for it, is dependent on the depth of your survey. So stay tuned for that. The other thing you should ask me about is other DM models. So Mariangela Lisanti, Isabel Sands, who are both here, and then Lena Nassib and Stephanie O'Neill we're all working on repeating a lot of these studies in other dark matter models. And you can ask me about my cautionary tales of SIDM. Thank you very much for your attention.